I always use syrup. If I have a choice, I would
there we go. Yeah. That one. Okay, yeah. I'll go through like our plan, like logistic plan now. That was my, because homework 0 is due after homework 1. But yeah, so yeah, right now it won't work because I have to update the link to it. Yeah. So just don't even worry about it. Yeah, we don't. Okay, welcome back. We made it to week number 3. It's pretty good. 20%, at least by the end of the week, we're 20% into the semester. 15 weeks, week 3, 1/5. So the things coming up are homework 1, finish up. So we have today and Wednesday. If there's anything that we want to either review, go back and review, or just kind of working through that. And then homework 0, we'll work on that one 16. Friday and Monday, and make sure. So I'll update, I have to update the website so that it gets you to the right links. Because right now when you try to do homework 0, it just brings you to like a dead web page. So I'm updating that right now. But was there a question? That was the question of like, how come it doesn't work? It doesn't work because it's broken, but I'm fixing it. I will fix it. The last step is just getting the links in the right, just organizing the website and then the actual connection to like our Jupyter server. So that one, that's the main things coming up. And then, oh wait, that one's Wednesday. Wednesday the 19th. I have to push off quiz 1 now that I'm looking at this. Because my brother is getting married like on Tuesday, the 17th. So I'm not going to be in class on Wednesday. And then, so we won't build quiz 1 on that Wednesday. So I'll push that one off. Sorry about that. I know it's always a bummer to have due dates pushed back. Like, I was so excited for this assignment that it was going to be done that day. But I'll push that one back so that we can actually spend time together on Friday thinking about like, what does this mean and how could I demonstrate these skills in a quiz format. That's what Friday the 20th will be. Kind of looking ahead 2 weeks. Good plan? No questions? Or I guess you do have questions, but do you want to, yeah.
Where's your brother getting married?
So he's getting married in Stratford. They wanted to have like a harvest moon wedding. Yeah, so it's the harvest moon. So that'll be pretty awesome. So they live there in Stratford, and then they're having like a big party on Saturday in Niantic. Yeah, it will be awesome. Yeah.
I like trying to do homework 0, it's like getting done. I went through like that page there and I submitted it, but I just like
Nice work.
Yeah.
Okay.
What's wrong with it? I don't understand.
Oh, what's wrong with it?
Yeah.
Okay. So in homework 0, what I had done at first was set up like it's supposed to, when you click Jupyter Hub, it's supposed to give you a copy of this page as a Jupyter notebook. But right now when I do that, it'll bring me to UGM ME lab with a frowny face. I'm like, we can't be reached because the site broke over the summer. And like I tried to go back in and fix it, but now there's like all these updates to Docker Compose and these things. I'm like, I can't. And I found a different way of hosting the website. So I'm working on getting that one up and running. Did you use this binder link?
No, I just got like a Jupyter like blank document. I just tried to like do the problems
Okay.
on there.
Yeah, so you can always like download this notebook like as a PyNV file and run it on your own computer, or you can upload it to whatever. There are places that run Jupyter Hub in different places. I guess I could also add a link to Google Colab, but we don't have Yukon Google accounts. But you could create like if you have your own personal account, you could launch it into Colab and run it from there too. So there's more than one way to interact with a Jupyter notebook. I was just trying to get like a one resource, like this is where you go, and we all have the same kind of computing box to work on. But yeah. Cool. Last time turned into just kind of like a long demo of me showing like how to plot things. Did you try this already, like plotting your results? Were you running into any problems? No. And then we had like a couple of more like textbook problems that we kind of skipped over with some questions about like what is, when you have differential equations, how do you solve them? What is x of t? These kind of things. So here's a question before we even discard that. Kinematic, if you're looking at things that are kinematic versus things that are kinetic, what's the difference? Like why do we have two words for these things? Are they both describing the same thing? Are they describing sometimes the same thing, sometimes something different? This isn't a homework question, but I want to know, what do you think? Kinematic versus kinetic. What is the difference? And you could tell someone else what you think if you want to like test it out on someone first. But what do you think? What is the difference? Kinematic, kinetic. Acceleration. Okay. We can write those up. And then, yeah, a couple people said energy so far. So like energy, kinetic, velocity, kinematic. What do you think? What is the difference? Yeah. Yeah. What did it say?
With force or without force?
Force and without force. Which one is force? Okay, so it's like a force is a kinetic thing. That's great. So we'll add that to our list. A force could be kinetic. Motion, kinetic.
Kinetic is the result of the motion.
And then kinetic is a result of
Yeah.
motion.
According to my research.
Yeah.
It was a ChatGPT, but yeah.
So if I know momentum,
I was thinking from the word. I'd say kinetic. I'd say kinetic. Right.
forces, so momentum. All right, so we'll do thumbs up, thumbs down. Is momentum a kinetic? Would we group it under kinetic things? Yes, thumbs up. So momentum is a kinetic thing. It describes kinetics, not kinematics. I'm just trying to get a sense of, so roughly, so we'll put it over there, over in moment. What about work? Kinetic? Is work a kinetic thing? And here, not like, man, this guy makes me do a lot of work, like actual force through a distance, like work, mechanical work. Kinetic? So a lot. Okay, so work. So then, so I agree. We'd split these things up in different ways, and it seems and I agree that this is a good split of like, if we're defining, if we have our definitions, some of them are kinetic, some of them are kinematic. What is the overall, like, what's the difference between these two? Like, what makes it kinematic? Why is acceleration a kinematic thing but not a kinetic thing? What makes it? Because a force is ma, right? Force equals ma. So shouldn't acceleration be also kinetic? What do you think?
You're kind of like a product of kinetic processes.
Okay, so a product. So this is like a result of the cause. So reaction, kind of the cause and the effect, maybe. That's one way to think about it. Cause and effect. What else? Yeah.
I think like kinetic, they can be grouped together, and kinematic ones can't. Like you can have like some of the force, but you can't have some of the velocity. Like you would really do that.
Well, you could have like some of the velocities. I mean,
but it would be like two different equations where like that one, those ones you can all put in the same equation.
Okay. Yeah. So yeah, coming back to like when you're looking for what causes things. It's like, all right, if I have a bunch of forces or a bunch of momentums, then I can sum all that up because I know there's some underlying conservation of momentum or Newton's second law, like something connecting it, something like that. Yeah. So generally, this is kind of like our causes of motion. It seems to be about what we're like circling around, right? Like these are describing like something about like how does motion happen, something about that, like a force is changing momentum or a force is creating acceleration. What about kinematic? What's connecting? What's like the underlying thing that makes it kinematic? Yeah.
Maybe like it's the motion itself.
The motion itself, like it's a description of motion, and we can describe these things like independently. Like our free body diagrams are like sometimes they're connected to the motion, like we're trying to figure out what motion is going to happen, but the forces exist independent of whether or not the thing's moving or not. Same thing like kinematic, we can define something moving in a circle without knowing what forces are causing the circle motion. And in general, kinematics is called like the geometry of motion. But it kind of like it's a general like description of motion, like some kind of equation that this is happening. And so when we say like kinematic equations, we're saying like this is the geometry of motion for something with constant acceleration. It's just that gets a little cumbersome to say every time you say kinematic equations, so it gets shortened down to kinematic equations. And like the general connection that we have in this class is always like mass times acceleration. So acceleration is again like some description of motion. And we don't have to know what the motion is to begin with. We just have to know that we're expecting motion and it's equal to whatever forces are there, whether those are constraint forces or spring forces, gravity, like it could be anything, but that's like our main connecting principle. If you get further into like either fluid dynamics or solid mechanics, like any of those, then you add more equations that connect like what's the connection between material motion and its like pressures or anything like that. But for now, all we need is that some description of kinematics, some description of kinetics, then we can connect the two. F equals ma. What about moment? Do you know what the moment is equal to? So a moment is going to be a kinetic description. Like we can solve for like how much torque there is and how much counter torque there is. We can figure out what constraints there are. What is that equal to for motion? Yeah. Yeah. So this is the sum of all the distances times like crossed with those forces. So we'll say like some point O. But what about our kinematic? Or kind of, well, I guess here it's kind of also a kinetic thing, but do you know what happens when you apply a torque? I guess like intuitively, if I twist something, what happens to it? Does it move forward? Like if I'm trying to change a tire and it's off the ground and I jam on it, like a big torque as I change the tire, what happens?
You get a centrifugal acceleration.
There's something spinning, right? Like things start spinning. So there's something, so there's got to be some way of like spinning motion and torque connection. And the main thing is like a change in angular momentum. So like there's momentum for how much it takes to push something, and then momentum for how much it takes to like roll something, like twist it around. So that one, the general form is like the change in H, which is kind of like not super fun, but just if you have a big, but if we had like 2 dimensions, then it would be the moment of inertia times alpha, like d theta, or d theta ddt, like d squared, dt squared. Like how fast this thing accelerates in a circle, like spins around. Like some kind of rotational thing. All right, quick aside. Just like what we're working on, like how these homeworks and these questions are all kind of connected. So when we were like solving those 3 free body diagrams and getting to that point of like x of t equals something, we were determining what forces there were using F equals ma, and then solving for, if we know a, we can integrate hit b, we can integrate hit x. That's kind of usually the same process for most dynamics kind of things. Sometimes dynamics is just only kinematics. Like, and some people that do like dynamics as a job, 70% of their job is just kinematic analysis. Do you know what that would look like? Like if someone said, we need someone to come and do kinematic analysis on our device or our robot or our car or this folding knife, anything like that? No? Any ideas what that would look like? Has anyone done like a kinematic? Maybe you have, but you didn't like label it. It wasn't part of your like general thought, like vocabulary. Like, am I doing kinematics today or kinetics? Like one kinematic thing that someone might do is just looking at like clearances, like a folding knife. I want the knife to fold, and I don't want the knife to clip an edge every time. So the knife has to, if the knife has to be a 3-inch knife or whatever, 2-inch knife, then the holder has to be more than 3 inches. And that's like simple enough kind of motion of kinematics. But then you might also want like locking, like it snaps into place, right? Some kind of kinematic locking. Now you can unlock and move back. But it's kinematics is usually just, again, like describing that geometry of motion. So it doesn't really matter how much force it took to get it in and out, as long as there's not kinematic interferences, like banging against each other. All right, cool. Back to the regular main content. What is the main content? What happened? Huh. And then, yeah, where were 2.9, 2.10? I don't know which one we were at. .210 was, oh, the luge model was 2.9, and then 2.10 is rocket lifting off. So I did want to come back to, it's been a while, but what would a free body diagram look like if I'm looking at the luge, the person riding on this luge, and they're coming, like I'm looking up the hill and they're coming around a curve. So they're up on the wall and coming around. What are the forces acting on this person? Like, just kind of looking at it as if it's a two-dimensional problem. Like I know they're traveling downhill and around a curve, but if we kind of just take a snapshot, like what are the forces acting this way in this plane? What does that one look like? Okay. Oh, okay. Yep. Yeah. So what's like ME and FS? Yeah.
This is the, so this is the first.
Okay. Okay. So he's on
Yeah,
the other wall. Okay. Around like this. Okay. 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 Like drag up the wall.
Like it's like.
So usually drag. Yeah, like if he was sliding. I think that would be thinking about like a skateboarder. So the drag. This one's a little weird. The biggest force, or the biggest like cross just straight out of the cage. Yeah, you're trying to figure out like what keeps it up, right? Yeah, something's gotta be there.
We're looking at it from, and this is the slide kind of further above.
This would be like the track is coming right at us. Okay. But that's going around the curve. Okay. So as we see the person, so if the curve is 0 curvature, then it'll be straight in the middle, moving straight down. That is, the more it curves, the more he slides up the wall.
Oh, okay.
I guess it could be he or she, someone in a helmet, but they are riding a luge. I know I only went to half the room, but check in on the other half for the next thing.
Yeah, we did.
So I saw like these two forces I definitely agree are there. Definitely some kind of weight. And then they're not traveling through the wall. So there's got to be some normal force forcing motion along the wall. But then the next step was people sort of figuring out, well, how could you actually be up on the wall without something? Shouldn't there be some kind of, like right now my resultant force is pointing down that way, so sliding down the wall. And if this person wasn't doing 80 miles an hour, kind of looking, so this is the front view of like just the curve. But if we look from the top, they're going around like some radius, and the tighter the radius, the more centripetal acceleration we have, which means the more centrifugal force we have pushing up along the wall. And this is enough, like as far as the free body diagram is concerned, these are the only two big things creating, like causing motion and constraining motion. And then all this is equal to like mv squared over r, if we want to look at centripetal acceleration. Yeah, as this person's coming around the curve, moving really fast. So we can set it up this way, where we have like some of the forces, and all we really wanted to do in these first couple exercises is just look at what are the forces that act on things. But if you're trying to figure out like how is this even possible, the missing part is that we have momentum, and that because we're changing the direction of momentum, that is another force that isn't captured in terms of what we're drawing in just that free body diagram. Now it's a callback. Now it's almost been like a week, almost a whole week or something since we did that, week and a half. So now 2:10. So we have rocket lifting off, and we want to add forces that include thrust, gravity, drag, and wind. It's a little weird to include wind and drag, but it's okay because we can separate these in. The way that I interpret that is like you're trying to lift off, but the wind is like there's a cross breeze. So you're going to be moving up a lot faster than the wind is blowing sideways, but it's still a small force that's acting. A small force that acts over a few minutes is going to have a big effect. So we do want to figure out what that effect is. So what does that free body diagram look like for a rocket? We need drag, we need gravity, thrust. Yeah. This one was 2.10, I think. Oh, yeah, it would be right here, right? 210. Not the wing, the wind. So far I've seen kind of like two forces opposing, one force going up. And I think this was like thrust for most people, that the thing pushing you up is your thrust. That's your main like driving part. Hopefully your thrust is more than your weight. That would be good. Otherwise takeoff would be very short. And then also the next thing that we'd have to worry about would be that like force of drag. So, and at some point we would just hit like a terminal velocity when force of thrust equals force of drag. But if we're taking off, then we're probably going like up into outer atmosphere, so drag keeps decreasing because it's a function of density. So as the air density gets smaller, we can move faster for the same amount of thrust. And the more we burn, the lighter we get, the faster we go. What if things are... What if thrust is, like, what if we're taking off, but we want to start changing trajectory? We want to start going at an angle. What does it look like now? What would stay the same versus change? Yeah.
MG would still be down with drag opposed thrust.
Okay. So mg still going down, and then thrust, or sorry, drag is now still opposite thrust. Yeah. Something like that. Yeah.
Aren't there different types of thrust on it that'll change its direction?
Different types of thrust.
You'll have
Like
thrusters on it to move it in a certain direction.
yeah. So usually, and like it is rocket science, so it gets pretty complicated pretty quickly. But one way you can control like your pitch of like you're taking off, but you're headed straight up, but you want to go at an angle. One way is just redirect the gas that you're expelling. So you keep burning at a constant rate or whatever predefined rate you wanted to burn at, but you have something that lets out more thrust on your right side than your left side. So now you're turning left.
So would direction be reliant on thrust?
So the main thing would be wherever you're going, drag is opposite. Yeah. So if you're pointed in a direction and you're trying to accelerate along that direction, then drag is also opposing that. But you could have cases, to your point, of like drag is like yeah, drag is still pointed straight down because you were going up, but you're doing like some kind of Top Gun maneuver of like do a flip and then hit the thruster. Yeah, I mean it's not. I mean in this like point mass, it's not super complicated yet, but there could be a case where we're changing direction of the thrust, but we haven't actually changed our velocity yet. Yeah. So we could have. So what we could do is have, if we want to account for all of that, kind of say like theta 1 is our thrust direction. Theta 2 is our like have two different angles. One where FD is always 1/2 rho times drag times area times V squared times V over V. So it's always wherever we're going, drag is always opposite that for, again, like maintaining the rocket science, like exactness of this. And this, oh, sorry, you can't even see it. Nobody cares. It's like he's just writing up formulas. Just let him keep going. All right, as we scroll up there. This is like if you have a vector divided by magnitude of the vector, you just get its direction. So just a fancy way of writing like the direction of that vector. Got 5 minutes left. Yeah, speaking of, all right, this one we'll set up the problem and then take a, because we're done in 5 minutes. Well, now 4 minutes. So I don't want to like spend the next 10 minutes trying to do the problem. So let's set it up. Then you can think about it. Go to sleep thinking about like Galileo and kinematics and kinetics and all that. So Galileo is known as like the father of kinematics because he's the first one that started to like put numbers and measurements to motion. And there's like all these different stories about him, but one of them was like he was using his pulse to time how long a ball took to roll down a ramp. So he was measuring time and displacement, figured out that displacement was proportional to time squared, the parabolic motion. So constant acceleration, kinematic equations, that's like Galileo's claim. So based on a few experiments, he figured out it doesn't matter how heavy or how light the ball is, like if it's gonna roll down a hill, it's always a constant rate for the same hill. But that's not true. Like it's true a lot of the time, but sometimes it's not. One example is like two skiers going down a hill that are going very fast a long distance. There's definitely a difference between an 8-year-old skiing and like a 40-year-old father skiing. There's a lot. There's a very big difference in how fast one is going to move versus the other. And then the impact at the end is also going to devastate the 40-year-old dad rather than the, yay, let's do it again. Oh, God. So the question is why? Why is there a difference sometimes, but not all the time, for a heavier skier? Because heavier skiers move faster down the mountain. And it's just, so why does that happen? Does it have to do with like the weight of the person? Because there's a couple of hypotheses that we can make. It's the weight, like the fact that there's more mass, gravity is a bigger force, so acceleration is bigger. That's one hypothesis. Do we think yes or no? Bigger weight, bigger A? Maybe, okay. That's opposite of what Physics 1 told you. Sorry, did you want to say something?
Less friction for the dad.
Less friction,
They speak
okay.
properly.
There's another hypothesis. Because there's more weight, so that would be more weight, bigger friction, though. Oh, but
No, I'm
less,
saying like, he's doing this way.
oh,
it's doing
versus
this.
pizza.
Yeah.
Yeah, pizza versus French fries.
Yeah.
This one, they're both doing French fries. Yeah, French fries. Yeah. So both of them have equal like friction coefficient, but different normal force. So one of them could be, another hypothesis is that bigger weight, bigger friction. So more weight, less speed. All right, anyway, did you want to say something? Tim?
Proportionate weight and area ratio.
Okay, so weight to area. So maybe like, so area might be another thing, that differences in area might change how fast you're going down. Okay, thanks. And I'll save these. Yeah. Oh.
Yeah, well, they do that, but they don't
Hey. Oh, sorry. I'll stop recording us.